This is part 221, line 19, a2a Semiconductor Heterostructures Schrodinger Quantum Confinement 5G Wow Seti. So this is the Wow Seti signal from 1977. That's the equation, and that's the answer to it, and there's the number. Go through Google for data for line 19. May 14, 2012. My thoughts: I found this keyword in another set of data and created a new video for it, just in case it's in details. Sorry. I don't know what I wrote there. I was trying to do more details because I didn't want to make the videos too long. There we go. Paraphrased. Keywords: heterostructures, wavefunction, quantum confinement, Schrodinger equation, and electron wave interference. So we're going to Google semiconductor heterostructures, quote data from a PDF file, imaging of quantum confinement and electron wave interference, Koichi Suzuki and Koichi Kanawisha. In quantum mechanics, matter behaves not only as a particle, but also as a packet of waves. The state of the matter can be represented by a wave function. By solving the differential equation of the wave function, called the Schrodinger equation, under certain given conditions, we can statistically estimate possible phenomena and obtain their time variations. The squared wave function corresponds to the probability of a particle existing. In quantum mechanics, there are three well-known fundamental phenomena: reflection of particle waves and interference when a particle collides with a potential barrier of infinite energy height. It is scattered elastically, energy is conserved. The incident and reflected particle waves interfere with each other because of their coherency. This results in a standing wave in the existence probability with half the original wavelength of the particle's wave function. Figure 1 is a tunneling effect. If there is a potential barrier with finite width and finite energy height higher than the particle's energy, the probability of the particle being transmitted through the barrier does not reach 0. I just keep yawning and yawning and yawning today. I don't know, it's the air in here. This effect is strongly enhanced for a thin barrier. Quantum confinement: when a particle is confined one-dimensionally in an infinite potential well, quantum well of width, the motion of the particle is restricted. Only the wave functions, called subbands, with wavelength of a equals that, and energy level of that, are allowed, where integer n is the subband index of that. Is the wave number, m is the effective mass, and h minus is Planck's constant divided by 2 pi. Figure 1 in C and D: if the barrier height is finite, these wave functions penetrate the barriers surrounding the well. So here are our figures here. I'll give you a little close-up of them. A, B, or C. I guess they were talking about all these. By the looks of it, that looks right. So figure 1, fundamental quantum mechanical phenomena: electron reflection and interference is A. B is the tunneling effect. C is the quantum confinement. I forgot D and E. Oh, C to E, sorry. Selected papers: forefront of basic research at NTT Basic Research Laboratories, imaging of quantum confinement and electron wave interference, Koichi Suzuki and Koichi Kanawisha. Abstract: we investigated the spatial distribution of the local density of states of electrons corresponding to the squared wave function by scanning tunneling spectroscopy on cleaved semiconductor heterostructure surfaces. We succeeded in imaging quantum confinement in a quantum well and electron wave interference at a potential barrier, which are fundamental phenomena of quantum mechanics. Our experimental method and results are encouraging for development of heterostructure devices with more precise performance through real space analysis of wave function. And they are from Japan, and their email is really tiny here. Let's make it bigger so you can look at it. There you go. And it's Koichi at will.brl.ntt.co.jp. So if you need to contact them about this thing that they did, you can. And we'll go on to our next video.